Okay. All right. Hello, everybody. It's Friday. Thank goodness. Let's finish section 3.1, and that'll be all we do today. So, we barely got started into 3.1 last time. We did the definition of a statement, in particular a logic statement. I'll often just say statement, but it's understood that we mean logic statement here. And we saw that a statement is a complete sentence that you can assign a truth value to. So it can be either true or false. Here I said is a complete sentence. Of course, it needs to be grammatically, a complete sentence, I suppose, that asserts a claim that is either true or false, but not both at the same time. Okay, so we can assign a value of truth to a statement. That's what we're looking for here. So how could a statement be both true and false at the same time? Well, we'll look at some of those. We'll look at some of those as well, examples. Okay. So let's just look at some first examples of statements, and then examples of non-statements, so things that are not statements. All right, sorry, 1 second. Okay. Alrighty. Can everyone see this color marker okay? My other classes didn't mind it, but just let me know and I can swap. I've got, I need to go get some more black markers, but is everyone good with this, or is anyone having a hard time seeing it?
No. It's fine.
Okay, cool. Okay, so an example of a statement here is the first, here's an example, the first even number is, let's say, is 3. That's an example of a statement. Now, it's definitely false, right? But that's okay. A statement is just a phrase that can be assigned a value of true or false. All right, come on, kid. Oh. Just sorry, I'm distracted. I'm home alone, and my roommate's cat is lonely, so she's trying to get up on my desk and stuff. Sorry about that. Okay, so the first even number is 3. It's clearly false, but that's fine because a statement doesn't have to be true, right? It just needs to be true or false. And this is an example of a statement that is false here. An example of a non-statement is the number 3 is the best number. Right, okay, so the number 3 is the best number. That's clearly that you can't assign a true or false value to that, right? Because it's an opinion, right? Okay. Some other examples. I think you're probably getting the point. Robert Bentley was a governor of Alabama. Y'all probably don't even know if that's true or false, but some of you might, but I believe that's how you spell his name. He was a governor of Alabama. This is an example of a statement that could be assigned a value of true. Okay, an example of a non-statement. Here's one the book gives. This sentence is false. Okay, so that's a non-statement because it's just not clear what the sentence is talking about, whether it's talking about this exact sentence or maybe a sentence prior to it. It's not a clear statement here. Okay. Now, we often, so this is pretty straightforward. We will often, or I'm just going to say we will denote statements using lowercase letters. So I might say, I might name these statements P like this, lowercase p with a colon, and then say a statement, the first even number is 3. Okay, so P could be assigned a value of true or false. Okay, and I could call another common letter we use is Q. We'll use P, Q, and R a lot. I could write the other statement there. Robert Bentley was a governor of Alabama. Okay. Just a little bit of notation there. In fact, I might use these this P and this Q later in some examples. Okay, another definition coming. We're going to get to some stuff that you actually get to think about and calculate, but first I got to get some definitions out of the way. And in fact, we might even skip example 1 because it's just about identifying statements, and I feel like it's pretty, the definition of statement is pretty straightforward. Okay, but a paradox, though, you may not know the definition of a paradox. A paradox is a statement that contradicts itself. Also called like a circular argument or something like that. A paradox is a statement that contradicts itself, and therefore has no value of truth, no single truth value. So it's not a mathematical statement because we want our mathematical statements or logic statements to be to only have one value of truth. Okay. Can I give you an example of a good paradox? Let's see, let me think. Oh yeah, here's a classic one. For example, I am a compulsive liar. Compulsive liar. Okay, so you may have come across a statement like this before, maybe even this one. Like, it's kind of like a joke, right? You know, it can't be true or false because, you know, this statement says I'm a compulsive liar, right? But the statement itself is a lie because the person is a compulsive liar. And so it's like circular. You can, you know, first it's true, then it's false, then it's true. It's true because it's false, and then it's false because it's true. And that's an example of a paradox. We're not going to do a whole lot with paradoxes. Pretty much just be able to identify them and say that they're not statements. That's kind of the point here. You can't assign. How would you assign a value of true or false to this? You know, okay. Alrighty. So looking at example 1 in the text, it says determine if the following are statements. I'm going to skip that one because I feel like I've talked enough about what statements are. I feel like you guys will be able to identify them. You can look at it though. Example 1 in the text, of course, they give you the solution, right? They give you the solution to the example. So if you'd like to look through it, everything they say there is going to pretty much parallel what I've been saying about statements. Let's move on to the next definition, get it out of the way, and we will practice using this one because some of these can be weird. A negation is like the opposite of a statement. But we say the negation, we don't want to just say opposite because opposite means like 50 different things in math, right? So the negation of a statement is the logical opposite of that statement. Now, what does opposite mean in like algebra? It means the additive inverse of a number, right? So like the opposite of 3 is -3. The opposite of x squared is -x squared, etc. So here we're going to be negating statements. So the next part of the definition here, I haven't technically finished the definition here. The next part should make a lot of sense. Negations, and what I mean by make a lot of sense is it should seem like an analogy to what opposite means in algebra. Negations always have the opposite truth value of the original statement. Okay. So if I give you a statement P and I tell you that the statement P is true, then the negation of P is false, right? So it should flip the truth value. That part's easy. What's not so easy sometimes is actually negating the statement itself, like in writing it out, like grammatically correct and everything. So we will practice that. But first, let me talk about some notation for negation. So we denote a negation by this little, let me redraw this so it's clear. This little tilde symbol, the little, it's called a tilde. I think I drew it upside down. It's actually like this, whatever. That's how we'll denote a negation. It's on your keyboard all the way in the top left if you're on a Windows computer. Or not a Windows, but not a MacBook. It'll be in the top left. I don't know where it is on a MacBook. Sometimes you might also see it written like this. If you ever see it like they might do that in the homework too. I'm trying to remember what Hawks does. Hawks usually does the same notation as the textbook, so I hope they do that. But if you see this little symbol, it's like a minus sign with a little leg there. That's a negation too. And these will be attached to a letter that represents a statement. All right, so let's do an example. So given P from earlier, which was P was the first even number is 3. Given P from earlier, find the negation of P. The negation of P. Well, P is the first even number is 3. So how can we negate P? How can we negate P here? The first even number is 3. So this one is going to be pretty straightforward. You may have already guessed it, just saying we don't want to complicate this. We're just going to say the first even number is not 3. Okay. Not introducing anything new into the statement, no other numbers, nothing like that. Literally adding the word not where it is grammatically appropriate. Okay. So that seems like super straightforward. But let's do some practice with some statements where we have quantifiers attached to the statements, and quantifiers mean they're talking about the number of things happening and negating the quantifiers. So let's look at example 2 so you can see what I'm talking about here. Example 2 from the text. Negate the following statements. Negate the following statements. This is where it starts to get a little interesting. So part A, I'm going to skip because you can go look at it later. You'll see it's pretty much exactly like the example I gave up here. It says Melanie is wearing a red raincoat. So the negation would just be Melanie is not wearing a red raincoat. Okay, so that's boring. We'll skip it. Alrighty. Here, these are the names of the statements. So statement B is the door is not closed. So the statement B is called, denoted by the letter B here, the door is not closed. Okay. So we want to negate B. The negation of B, my symbol got a little squirrely there, but it's the negation of B. Okay, so if we add the word not in, it's going to be the door is not closed, right? But that's like a double negative, and then in the same way that a double negative in math cancels out, they'll cancel out here too. So all we're going to say is the door is closed. The negation of B will be the door is closed. If the statement B starts off the door is not closed, the negation will be the door is not closed, which logically just means the door is closed. Okay. Here's example, or rather statement C, none, now this is the first interesting one. None of the tourists brought raincoats. None of the tourists brought raincoats. Okay, what is the logical opposite of none of the tourists brought raincoats? So you might be, yes, Kevin, go ahead.
Would it be all of the tourists brought raincoats?
Not quite, because there's more to it than that. There's more that we can say. So we want this to be the opposite, right? Rather, negation of C to be the opposite of this. So I'm going to draw a little picture here to help us figure this out, because this is important. This is an important thing to talk about here. So let these blue dots be, no, let's say actually, let's let these red dots be tourists who did not bring raincoats. So C, the statement C says these tourists, these 5 tourists, none of them brought raincoats. So red means none, red means no raincoat. Okay, so that's what C is saying. But then can't the negation of C, and let me say this here, blue means raincoat. Get that written down. Can't the negation of C be something like this with one of them, right? Because if one of them brings a raincoat, then now C has the opposite truth value, right? It's no longer true. Over here, C is true. None of the tourists brought raincoats, but as soon as one of them, as soon as one of them brings a raincoat, then now C is false. And what about if 2 of them? Then C is still false, right? And what about if 3 of them? Then C is still false. And 4 of them, C still becomes false. And then the one that you said, Kevin, if all of them bring raincoats, then C is still false. All of these are the logical opposite of none brought raincoats. If 1 brought a raincoat, 2, and why is this? Because the statement none of the tourists brought a raincoats is a pretty strong statement. If you wanted to confirm the validity of this statement, you would have to look at every single one of them and see, do they have a raincoat? So for this statement to be wrong, only at least one person has to bring a raincoat. If I say none of these people brought a raincoat, but then we look through all of them and I find and you find at least one that does have a raincoat, then this statement is false, meaning its truth value is flipped, meaning if its truth value flipped, we need to include all of these in its negation. Okay, so long story short, how do we say that? We don't want to say all of the tourists brought raincoats because that's only this category here. We want to say at least, oh, excuse me, at least one tourist brought a raincoat. Yeah, I told you it would get a little bit more interesting with these quantifiers. So when I say quantifiers are the little part attached at the beginning of the statement that tells you like how many things are going on. Like none is a quantifier. All would be a quantifier. At least one is a quantifier. You could also say some, like S-O-M-E. The word some is a quantifier. So here we could also, I guess if we wanted to be, you know, a little bit more vague, we could also say some of the tourists brought a raincoat. But really, this is the most correct thing to say, that this gets to the point that at least one tourist brought a raincoat. And this negation of C here, that includes all of these. That includes all of these. All these categories I drew down here. Good. Now, before I move on to statement D, which is also interesting, and it connects to this idea. There is a table on page 91. That talks about negating quantifiers, and that may be helpful. It kind of just gives you the grammar for it. Oops, negating quantifiers. And it has the category that we just looked at. It says if your quantifier is none, then your negation should be there is at least one. Okay. All right. So that would be a big point to write down here. The negation of none is at least one. Let's see, I'm gonna go to a fresh sheet here, continue working down this way. Statement D. Now here's another chance for you guys to think about this. It's in a slightly different way. Here's a statement: I run less than Kara. Okay. I run less than Kara. Okay. I want the negation of D. I think I always draw my negation symbol upside down. It's just like more comfortable doing it that way, but you can tell what it is. Okay, so the negation of D. Well, if Kara, like, let's assign some numbers here so we can get our minds right. And if Kara runs 5 miles and I run 4 miles, then, you know, this statement is true. So you may be tempted to just say I run more than Kara, right? But don't I also need to include when I run the same as Kara in my negation? So if I run less than Kara and Kara runs 5 miles and I run 5 miles, then this statement no longer is true because I've run equal to her, or equal distance, right? So my negation here should be I run more or equal to. I'm trying to get this to be grammatically. See, sometimes you figure it out and you're like, okay, now how do I make this English grammar work? Let's just say I run the equal, we'll just say same as the same distance, I suppose, but we'll be just as vague as they were up here. I run same as Kara. Let me say the, okay, start over. I run the same as Kara or more than Kara. So again, your instinct is partially right. I'm assuming most of y'all's instinct would be just to say I run more than Kara. So just like earlier, when Kevin said that his instinct told him the negation of none would be all, it's partially right, but there are cases that we need to consider. And in the negation of C, the way to get all the cases was to say at least one for the negation of none. Now, if I say something is less than something else, and I want the negation of it, then I have to say the same as, so equal to or more than, not just more than, but equal to or more than. So in symbols here we go. Here we go. Let's see if we can put numbers to this. This would be nice. The sentence D is saying I run less than Kara. Let's just say my distance is X and her distance is 5. Then the statement is X is less than 5, right? X is less than 5. The negation of this thing, this is X is bigger than 5, right? But also equal to. X is bigger than or equal to 5. So this is kind of like the math symbol way of what description of what I just said here. I run the same as or more than, greater than or equal to, right? Greater than or equal to Kara. Okay. All right. So negations can get a little weird. Something to be careful of. If you see quantifiers at the beginning of your statement, you're going to want to take a second and really make sure that you're understanding it. Maybe draw a picture. Consult that table too on page 91. All right, now let's move on to talking about compound statements. Compound statements. This is where it's going to. This is going to be the basis for what we're going to talk about in section 3.2 and 3.3. A compound statement all it is a statement that is composed of more than one, so two or more statements. So the statements we've been looking at, but how do I stick them together? It's composed of two or more statements, and how do I add them together? Well, there's a few different ways I can add them together. They can be joined together. Now, how do we join things together in math? Well, we have addition, subtraction, multiplication, division, and other ways as well. But how do we join together words like statements? We say with other words, such as the ones we're going to look at, the word and, the word or, and the word implies. And where we're going to culminate with these is looking at the truth values of statements that have been connected in this way. So the truth values of compound statements, that's where this is going to get interesting. But first, let's just look at some examples connecting these statements into compound statements. So let's say the statement, I'm going to give you a new statement P here is it is raining. It is raining. And Q is it is sunny outside. Okay. Can we connect these statements using and, or, and implies? Sure, no problem. You literally write one, then you write the word and, then you write the other one, or the word or the word implies, and just make sure it makes grammatical sense. So P and Q will be, it is raining and it is sunny outside. Okay, so do I really need to write all of these? I think you get it here. But one thing I will say is that we have little symbols for these. We actually will never write this as I've written it here. We have little symbols for these. We have the upside down capital V looking thing. This is used to denote the word and. The capital V looking thing is used to denote the word or. And the double-sided arrow is used to denote implies. And you literally read them as and or implies. So if I said find P or Q, that's how you read that, P or Q. So you would say it is raining outside. Oops, raining outside, or it is sunny outside. All right, now we're not worried about whether this is a true or false statement, right? Because we don't know if it's raining outside, right? I mean, in this fake, make-believe world here, we don't know if it's raining. We don't know if it's sunny, right? So the point is to not, right now, the point is to not be thinking about, is this a true or false statement? Could it be true? If both are true, like, could it be false? Like, we're not there yet. We're just practicing connecting them. In a minute, well, actually in the next section, we're going to talk about how to connect the truth values of these two distinct statements. And once we connect them with these different symbols, these different connector words, what happens to the truth value of the statement overall, right? So we'll look at that. But all right. Example 3 in the text says using logic symbols for compound statements involving and. So really, well, and example 4 is for or, and example 5 is for implications. I'm gonna skip example 3 and 4 because, again, I feel like they're pretty straightforward. Hang on one second, I need more paper. I'll give you an idea of what's going on here so you can see why I'm skipping them. Example 3 says, I guess I'm writing it anyways, that's all right. We have time, we're gonna get done early today anyways. Example 3 says to use the following simple statements A and B to symbolically write the given compound statement C. So if A is snow is falling, and B is the sun is shining. I should put a period there. The sun is shining. And C is snow is falling and the sun is shining. How can you write C in terms of A and B, like literally with the letters A and B and a little symbol in between? Then you would say, well, the first part is the snow is falling, so that's A, and then there's the word and, so there's that symbol, and then the sun is shining is B, so okay, so pretty straightforward, right? Cool. I could also sneak little words like not in here. I could say snow is falling and the sun is not shining. What would that mean? That would mean that I would put a little negation symbol on B. Maybe that's a good one to write down. So if I added something to this example, let's say a new statement D. So what if the statement D is snow is falling? Okay, so D equals snow is falling is A, and so that symbol, the sun is not shining, but that's the negation of B. So I would say negation of B there. Cool. Just putting the symbols together there. Example 4, very similar, except it's using the word or. So you just got to remember for and, it's pointing up. For or, it's pointing down. I am going to do example 5 though, because example 5, the implications symbol, you got to understand how those work, and they are actually really important too in beyond this class in math and just and at the top of this chapter I mentioned that we would look at common logical errors, and the implication compound statement is going to be where a lot of those common errors happen, and I'll probably be able to catch a lot of you making that error when we talk about it in section 3.2. That'll be kind of one of those like light bulb going off moments. So I want to not skip example 5 because it is about these implications. So the instructions say use the following statements S and T to symbolically write the given compound statement Q. Okay, so same instructions, just new statements, and they're going to be connected differently. The water temperature on Saturday is below 76.2 degrees, probably Fahrenheit, but they didn't tell us, that doesn't matter. And T, you are allowed to wear a wetsuit. Okay, you are allowed to wear a wetsuit. What is it in the triathlon? Okay. Oh, I spelled it wrong. There's not a first O. Triathlon. You are allowed to wear a wetsuit in the triathlon. And the statement Q is a compound statement. It says if the water temperature, now if you don't want to write all this, what I'm writing is on in the textbook in example 5. So you could just write for reference example 5 and then probably just write the solution to it. That would be fine too. If the water temperature on Saturday is below 76.2 degrees, comma, then you are allowed to wear a wetsuit. Now earlier, to wear a wetsuit, I said that there's the word and, the word or, and the word implies, right? And I gave symbols for those, and I said those are going to be what we look at to connect these simple statements. But here we're not seeing any of them. How are these connected? Well, they're not connected in the center necessarily. They're connected by if and then, right? There's this word if at the beginning, and then right here. So if is before the statement S, and then is before the statement T. So the point is here, if then statements are the same as implication statements. So implies implication statements. So if this, then this is the same as saying this implies this. So let me write that down. If A, then B is the same as, so I'll just say equals A sorry, I wanted to write it in words. A implies B. I'm so used to writing it in symbols. Okay. If A, then B is the same as A implies B. So what I'm telling you up here for this example is that Q is going to be S implies T, right? And the order very much matters here. I have to make sure I'm doing it in the right order, and S is clearly first and T is clearly second. So that means Q, and now in symbols, Q is equal to S implies T. That is going to be one of the most interesting statements that we pick apart their truth values later on. So a little bit, it's going to be a little bit counterintuitive, but that is all I wanted to do. On page 94, there's a nice little table with all the logic symbols. If you'd like to have that for reference too. I wrote all what they all mean, but if you want it all in one little place in your notes, you could go copy that table from page 94. Let me give you some problems to look at, which I need to actually find. Let's say number 13. So let me write 3.1. So these are just problems to mark for review. Let's say 13. Now this, honestly, this section it's important, but really it's kind of building up to the next two. So I'm not going to give you a lot here. Just want to make sure you know how to negate things. So let's say 13.25. How to use these symbols, how to negate things. 31 would be good too. 31. And remember that the answers to these are in the back of the text. Ooh, and let's do 35 as well. Oops, 35. I'm circling them in my textbook too, so I know which ones I'm telling you. 35. And we can always talk about these because 31 and 35 might be a little tricky. So we can talk about those on Monday. That's all I got for y'all today. So you guys are good to go. Stick around if you have questions.